Okay, let's start class. So we will finish the generalized linear model today, and we will start uh, the nonlinear smoothing and the generalized additive model today. Okay. So the last topic for the GLM, generalized linear model, is this rate model. Okay. So what is a rate model? Sometimes we know that like Poisson distribution is about the count. But sometimes the count data depends on some size variable. For example, let's say it depends on the population size. Like if we are talking about the cell volume of a certain product, but that cell volume is related to the population size in that city, right? If we have a large population volume, of course the large population size, of course, the cell volume will goes up. So something like that. So that is related to some size variable. So instead of modeling the count itself, maybe it's better to model through the rate. That's the count divided by the size variable. Okay, so I will show you one example. So here, oh, here this is a dicentric data set in the faraway library. We have 27 observations. Okay, so this study is to conducted to determine the effect of gamma radiation on the number of chromosome abnormalities. Okay, so we have the cell numbers. So that's the cell number of cells in the hundreds. And the CA is the chromosome abnormalities happened. Okay, and the dose amount and the dose rate. These are the two treatment. So that we are focusing on. So we want to see the dose amount and dose rate effects on the number of chromosomes that occurred abnormality. So CA is the count. These two are the treatment, but this is the size variable because the cell chromosome abnormality, this one is related to the number of cells, right? If we have large number of cells, of course, the number of chromosome abnormality will go higher, right? So this is an example to use the rate data. So let's first check this table. So here I use this line to show the ratio of the cell abnormality divided by the number of cells. So through the dose amount and dose rate. Okay, so you can see the dose rate, first row, dose amount, first column, and these are the ratios. Okay, okay, let's see the plot. So this is the interaction plot, and you can draw this plot through this code. Okay, so you can see here we have the horizontal axis is the dose amount. So this is the dose amount. We have three levels, 1, 2.5, and 5. Okay, and dose rate, I use different line type to show the dose rate from 4 through 0.1. So these are the different dose rate. Okay, so the vertical axis shows the mean of the cell abnormality divided by the cell counts. Okay, so you can see here through this plot, you can see there is a, it's not additive effect. It's not. It's multiplication effect. Do you see that? Why? Because if it's additive effect, what does the interaction plot looks like? If it's additive, it should be like these, 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 something like that. It should be parallel. But since it's, so it will be close to the parallel. But here, the multiplication effect is, you can see when the dose increases, dose amount increases, and also with the dose rate increases, that effect is much larger than its own effect. The sum of its two effects. So you can see there is a increment, not from the addition, but from the multiplications. Okay, so through this, we would like to use what? If we see there is a multiplication effect, we would like to use the log of the dose rate. Okay, so here, so we first fit a Poisson model with the, so we have the response is the cell abnormality, and we have the log cell. So I put the log cell here. I will tell you why in a minute. This is the size variable, right? This is related to that, but here I first included as a log cell. Then I have the log dose rate because we see some multiplication effect. And also the dose, that's the dose amount, okay? So here, I use the Poisson as a family. Okay, so you can see here we have an intercept, we have the log cell and the log dose rate, and we have the log dose rate times the dose amount. Okay, and you can see here the log cell has the coefficient is very close to 1. Okay, so remember what is the, for the Poisson regression, what is the link function? The link function for the Poisson distribution for the Poisson regression is log. Log of the y can be modeled by, let's say, beta 0 plus beta 1 x. So the link function for the Poisson regression is the log. So here, instead of modeling the count, we should model the count divided by what? Divided by the cell size, CEL, right? So instead of modeling the count, we are modeling the rate. Okay, so it's log rate. So what is the log rate? So the log rate is just the log y minus what? Log cell. Is that right? Because the ratio within the log is equal to the subtraction between the two logs. And then if we move this term to the right-hand side, it becomes what? So this model just becomes to what? Just becomes to the log of the y equals the log cell plus the beta 0 plus beta 1x, right? So you can see we have a term called the log cell here with the coefficient is exactly 1. And this is exactly the here. You see, the coefficient is very close to 1. So this implies what? So this term has the coefficient is very close to 1. So this implies instead of modeling the cell counts, the number of cells that has the abnormalities, we should model the rate, which is the CA divided by the cell. You see that? So this step, so this model is just to convince you that we should include the cell as to model the rate instead of CA, instead of the count. So then we fit still the Poisson model. Now this time we have a term called offset for the log cell. So what is an offset? Offset is a special term in the statistical model. So that offset is moved to the response. So instead of modeling the log of the cell abnormality, we model the log of the cell abnormality divided by the cell volume and equals to the x beta. So that the offset means that the offset of log cell means that we are actually fitting this on the left-hand side using the x beta as the linear model. So this is the response and this is the linear part. Okay, so so this is called offset. So in that way, when we do this, so log cell does not appear in the model output because it's already included in the part of the response variable. Okay, so we have the intercept, the coefficient for the log of dose rate and dose amounts and interactions. So you can see all of them are significant. So you can check the deviance. So here the no deviance is that. So what is the no deviance? No deviance is the deviance when we only have, the intercept only model. So the no deviance shows the deviance for this model includes this equals the beta zero model. So this no deviance shows the deviance of this model. What is the residual deviance? Residual deviance shows the model that is the left-hand side is still the same, but this time we include the beta zero plus the log of the dose rate plus the dose amount plus the interaction. So that full model. So you can see what is the proportion of deviance that has been explained through the models. So that is over 99%. So that shows an effectiveness of including the cell size as the ratio. Okay, so we model the ratio using the log of the dose rates and dose amount and their interactions, and we got the portion of deviance has been explained is over 99%. Okay, so this is a example for the rate model. Okay, so rate model has been used a lot in practice. So sometimes when we have the size variable, we use the rate. Okay, like here, there's another example. So if we recorded the number of car accidents in different cities, okay, so it's better to what? It's better to model not the number of car accidents, but the number of car accidents divided by the population size. So that's the rate. It's better to model the rate, right? Because we know the big city, of course, has much larger number of car accidents. Like to model the number of car accidents in New York is much higher than the number of car accidents in New Orleans, right? Because the size are very different. Okay, so any questions? Okay, so we finished the generalized linear model. So we will go one step further. So we will move to the generalized additive model. So this is an extension of generalized linear model. So why? Because for the generalized linear model, we have a term called linear, right? So it's a linear. So the systematic part is a linear part. But this one includes, we can have the nonlinear part. Okay, and also it's still generalized. What does that mean? That means the response variable, as long as the response variable falls into the exponential family, just like the generalized linear model, we can do the generalized additive model. But we can actually include nonlinear effects. So that is more flexible. Okay, so we will talk about that. But before we move to the GAM model, GAM model, we have to talk about the non-parametric regression first. So what is that? That is a nonlinear regression for one variable. So it's a GAM is an extension for the GOM through the including the nonlinear effect. Okay, but how to have this nonlinear effect? So before we talk about the GAM, we have to talk about something that shows the nonlinear regression through the non-parametric regression. So that's the outline. So we will have today's class talk about the non-parametric regression, and Thursday's class we will talk about the GAM model. Okay, so this is our plan. So non-parametric model. So in the traditional regression analysis, the form of the regression function has been specified. Okay, for example, we can have this as a linear model. Okay, so you may ask, wait a minute, this is not a linear model. This is a polynomial model, right? But in statistics, we can still consider as a linear model. How do we consider as a linear model? So here we have the y equals to beta 0, that's the intercept, plus beta 1x, right? What about the second term? It's a quadratic term. But you can consider, let's say, this as a new variable called z, x squared as a new variable z, right? And you can consider the x cubed as a w. So if you consider x squared is z, x cubed is w, then it's a multiple linear regression. You see that? So that is still we can consider as a linear model through the for the polynomial regression. However, in some situation, we don't have enough information to make an assumption like this. So we may just want to assume y equals to x fx plus epsilon, where the fx is just a smooth function with first and second order derivatives. So this is a very general assumption. Can we have that? Yes. And that's this type of regression, we call it non-parametric regression. Okay, so in statistics, there were two places that we use this term called non-parametric. First place is when we do the hypothesis test. You may heard that, oh, in statistics, there is a group of tests called non-parametric test, right? If you heard that term, that means we are not doing like a F test, T test, Z test, chi-square test. No, we are not doing that. Because all these F test, T test, Z test, chi-square test, they are related to what? They are related to some assumption, distributional assumption. Like we assume that the population follows a normal distribution so that we can do two-sample t-test. So that's called a parametric test. So non-parametric test means that this test does not assume any distributional assumption. Okay, so that's one thing. Another place that we heard non-parametric test or non-parametric word is here. Non-parametric regression or non-parametric models. What does that mean? That means we do not assume any specific functional form between the response and explanatory variable. Okay, so here, like this one, This is parametric regression. Why? Because we assume that there is a cubic relationship between the x and y. So the model has to have beta 0 intercept plus a linear term plus a quadratic term plus a cubic term. We have to specify in that specific form, and that's a parametric model. What is a non-parametric model? Non-parametric model is like that. Y equals to fx plus epsilon. We didn't assume any parametric form of f. As long as f is continuous, differentiable, that's fine. But is f a sine function, or is f a quadratic function or cubic function? It doesn't matter. We are not having any constraint on this f. So we have very flexible assumption. So that's called the non-parametric model. Okay, so that's what it means. So as a simple example, this is the battery voltage drop example. You can see the horizontal axis is time and the vertical axis is the voltage drop. We have these observed data points as a red dots. Okay, so how to fit that? First, let's just fit a cubic model. So what is a cubic model? This is a cubic model. So this is a polynomial regression with the highest order is a cubic order. So is this a good fit? Maybe the R square is quite large, maybe 80%, 90%, something like that. But if we look at the residual, so this is the residual. So you can clearly see that there is a systematic non-linear trend in the residual. Is that right? You can see a W shape in the residual. So that means what? This is not a good fit, because if the model fits the data well, what does the residual plot looks like? It should look like random, entirely random. There's no systematic shape. Like here, I increased order to the quartic order. So we have a fourth order term. So then the residual looks like that. That looks much better because we didn't see any nonlinear systematic deviation from the pure random, right? So this seems to be a better fit. But this example just shows that in reality, it's not easy for us to find out a good parametric model. So this one is lucky. We just find out, oh, so the fourth order term is good. But in reality, if you give me a data set, I may not be able to find that, right? So what should we do? So instead of modeling through this quadratic model or the cubic model like that, we can have some other choice. Now, here is some other options. First is the piecewise polynomial. So instead of using the quadratic model, we use piecewise polynomial. So first, what is piecewise? Piecewise is opposite of this model. This model has another name called global model. Global model. So why it's called global model? Like here, we have this cubic term, we have this quadratic term, we have this quadratic term, linear term. So all these will impact all the x values. Is that right? So if, let's say, I increase the beta 3 by 1, so by just this change on the beta 3, that will affect all the data points. Is that right? So that's why it's called a global model. Global model means that every term will affect all the observations. Okay, so what is piecewise model? Piecewise model is not global model, is local model. Okay, so let's see. So here I have the piecewise constant model. So why it's called a piecewise constant? So let's say this is the range for the x. Okay, this is range for the x. So here the circles in the background, these are the observed data points. So instead of fitting one global model, I fit by the piecewise constant. Okay, so that's one way. But is that a good model? No, it's not. Right? Now I get a little bit complicated, called a piecewise linear model. Is that a good fit? No. Why? Because there is an abrupt change at these two locations. And these two locations has a name called knots. KMOT. So we have two knots here. So these knots are set the range for the piecewise linear or piecewise constant. So it's not continuous at the knots, right? So now let's say now we put it as a continuous piecewise linear. Can we do that? Yeah, this is better than this, but still no good. Why? Because although it's continuous, but it's not differentiable at these two knots. Why? Because you can see abrupt change at the knots, like the derivative below the C2 is negative, but the derivative right above the C2 is positive. So there is an abrupt change in the directions. It's like a broken chopstick. It's connected, but it's not smooth because of the first order derivative is not continuous. Although the function itself is continuous. Is that right? So we still don't like that, okay? So you may ask, how can we model these continuous piecewise models? Very simple, actually. It's much simpler than you think. To model this piecewise linear model, we only need some basis. We call it basis. That basis is the piecewise linear basis. So like here, this basis is called x minus C1 with the plus sign in the subscript. So what does that mean? That plus sign in the subscript. That plus sign in the subscript only records the positive part. Okay, so what does that mean? That means if x is less than C1, if x is less than that, x minus C1 is negative, right? If x is less than C1. So, but this only records the positive part. If it's below zero, always zero. So that's why it's constant. It's a constant zero when the x is below C1. But when the x go beyond C1, then it will just show its own value. So this has a name also called the broken chopstick basis. Okay, so it only records the positive part. If it's below zero, it's always constant zero. So if we're using this basis, you can see we can have the piecewise continuous linear function using these four bases. Okay, so the first term is the intercept term. We know that. The second term is the global linear part. Why it's called global linear part? Because the coefficient for the h2x, which is the linear function itself, will affect all the observations. So that's why it's called a global term. But these two terms are local terms. Why? Because they only affect part of it. Okay? For example, you can see why this is called a local term. Tell me. Because it's always zero when the x is less than that. So in other words, the coefficient, let's say this has a coefficient is beta. So the beta, if I make some change on the beta, will that have impact on all the observations? No. It won't. It will only impact on the observations which has the x is what? Has the x is greater than C1. Because if it's less than C1, it's constant zero. There's no effect. You see that? So that's a local term. Okay, so by including these four terms, we can have a continuous piecewise linear. But piecewise linear doesn't look very good, right? It's connected, but it's not smooth. So let's go one step further. Piecewise polynomials. How about that? Okay, similar idea. Now this time, let's say we have a discontinuous piecewise cubic polynomial. The cubic polynomial is this model. So we have the x term, x squared term, x cubed term. Okay, so piecewise cubic polynomial, but discontinuous. That no good, right? But this one continuous, but you can see just like the previous one, it's not smooth at all. So this is continuous for the first order derivative. So this one is much smoother than this one. Continuous on its raw value as well as the first order derivative is continuous. But this one is much better. This one is the continuous second derivative. So this one is continuous in f function itself, as well as the first order derivative and the second order derivative. Okay, so you may ask, how do we get that continuous second derivative? Still not difficult. It's similar idea as before. So we have these four terms, and these four terms are global terms. And I think you can easily recognize that. The first one is the global intercept, global linear, global quadratic term, global cubic term. So these four are global terms. We have two local. This is the x minus c1 cube with the positive part. This is x minus c2 cube with the positive part. So by including these six terms, we can have a continuous second derivative for the cubic polynomial. Okay, so you may ask why we stopped here. Why we not have the third derivative continuous and so on? Okay, because here, let's see. Did I show it somewhere? Let's see. Did I show it? I think I. Interesting. Okay. Anyway, so here, the reason we stopped at the second derivative is that there is some study from the people that our human eyes most of the time will see the discontinuity up to the second order derivative. If a function is continuous in itself plus the first order derivative and second order derivative, then most of people, 99% of people, will not see any discontinuity in the third order derivative or more. So that is the best. So that is the simplest. In other words, this second order derivative continuous is the simplest function that we can have, that human eyes cannot see any discontinuity in the third order derivative. In other words, if we take a third order derivative, this function is not continuous. But human eye, most of people, human eye cannot recognize that discontinuity. Okay, so that's why this is we stopped here. And plus, if we have the continuous third order derivative, we will have more bases. So the function will be more complicated. Okay, so after we talk about that, so these fixed knot splines that, as I showed here, there's a name called the regression splines. So in practice, it seems to us regression spline is good enough, right? But there's some criticism, okay? The criticism is what? One needs to, if we use that, we need to choose the order of the splines, the number of knots, and their placement. So here, you may ask, why we need to have 2 knots? Why not 3 knots? Why not 4 knots? And why we use cubic polynomial? Why are we not using the quadratic polynomial or the quadratic polynomial, right? So these are the valid questions raised by people, right? So these introduce some subjectiveness, okay? Especially the placement for the knots. Why we need to have 2, not 3, 4, 5, and why we have to put it here, not put it here and here, right? So one simple approach is to parameterize a family of splines by the number of bases or degrees of freedom, so that can automatically chosen. Okay, so here let's talk about another spline called the B splines. So in the B splines, which is very similar to this, okay, I will show you the basis in a minute. In the B splines, we actually can get a basis matrix for the cubic splines evaluated at n observation in the X. With, we can define the number of interior knots through the degrees of freedoms. And these degrees of freedom by default, if you don't specify the location, it will just split at the percentiles. Like here, for the cubic spline, okay, we have 7 degrees of freedom. So that means we have 4 interior knots. And you may ask why we need to minus 3? Because the cubic spline has 3 terms except the intercept terms. So we have 3 terms. Why? What are the 3 terms? Linear part, linear term, quadratic term, and cubic term. So these are the 3 degrees of freedom for the global. Remember the basis? We have 1, 2, 3. Besides the, so we didn't consider the intercept. We just consider these 3. So we have 3 degrees of freedom for these. Okay, so that's why we subtract 3. And then we got 4 left. So that means we have 4 interior knots. So where to place? We place it in the 20 percentile, 40 percentile, 60 percentile, and 80 percentile. So why? Because if we have 4 interior knots, okay, so we basically split the data into 5 parts. The 20s, 40s, 60s, and 80s. So by setting these 4 knots, we have these 4 or 5 regions. Each region contains the same amount of the data points. Remember, this is not equally spaced. This may not be equally spaced. This just shows each region contains about the same number of observations. Okay? Of course, here you can specify if we use a cubic spline or not. If you want to use a linear spline, not cubic spline, then you can just set the degree to be 1. But by default, the degree is 3. Okay? And so the B splines allows efficient computation even when the number of knots is large. So the good thing for the B spline is it is computationally efficient, and you only specify the number of degrees. You only specify the degrees of freedom. It will place the knots based on the percentiles. If you don't specify the specific location for the knots. Okay, so let's see. This is the B spline basis. So you can see I use different colors. Okay, so these are the local bases. you can see the first one is that on the left is this one. So this term only has effect through from 0 to about, let's say, 15. When the x is between 0 and 15, it has an impact. But when the observation has the x value outside this range, it's all constant 0. It will not have any impact, right? And the next basis is this one. You can see this has the basis ranged from 0 to about 20. So it only impacts the observation that has the x is between 0 and 20. Outside this range, constant 0, no effect, and and so on. So you can see all the bases from the B-splines are local, only in affect the observation with a certain range of x values. And also, these are the cubic B-spline bases. So each function itself is a quadratic function. So every basis function is a quadratic function. Okay, so now we have another spline called the natural spline. Okay, why need to have another spline? We have the regression spline, and we improve something through the B spline. Now we have a natural spline. Why? Because a natural spline is really useful when we comes to some extrapolation problem. Okay, so what is extrapolation? Extrapolation is that, let's say, suppose in our data set, we have a training data. In the training data, we observed x from 0 to 100. Okay, and we can fit a model. Let's say the model is linear. Now, when we do the prediction, we have some new x, which is outside the range of 0 to 100. Let's say we have some new data points, which has the x is equal to 120, which 120 does not appear in the training data. And in that case, the prediction on this particular point is called extrapolation, because it's outside the range from the training data. And that's very risky. Okay, not good. But what are good? That if we have some new data point we want to predict is within the range. Let's say I want to predict some x which has the x value is equal to 60. That's good because our data includes some points is from 0 to 100. So 60 is falls into the range in our training data. So that is called interpolation, not extrapolation, called interpolation. Interpolation. So interpolation is safe and good, and you can predict with confidence. But extrapolation is risky, not good, and it can be misleading. Okay, so the problem for the B-spline is that it will be very, very dangerous if we do the extrapolation. Why? Why? Because it has the cubic spline, right? If we use the cubic spline, it has the cubic spline on the boundaries. Okay, think about we have the data we observed is have this range. Okay, so we modeled through that. Let me. So if we have the training data has the data points which is in this range from 0 to 100, right? Let's say, okay? And we fitted a cubic model. Okay, now we have a data point which is 200. What is our estimate? the estimate goes, it goes cubically fast. It will be much, much larger than the other points. But however, maybe the true function is just like that. It fits well within the 0 and the 100 in the cubic model. But outside the range, it should go with that way. But the cubic model goes much faster. So you can see we have a huge bias from the cubic splines. You see that? And that phenomenon is we statisticians observed that many, many years ago. The cubic model or polynomial regressions has some very risky effects if we do extrapolation. Okay, so that is in statistics called the boundary effect. If you heard, okay, our model has a boundary effect. That means if we have an extrapolation problem, the results can be very misleading. So the performance outside the range of the training data can be performed very weirdly, and the results can be horrible. Okay, so that's called the boundary effect. So the natural spline comes to the rescue. So natural spline has a constraint that outside the range, outside the boundary, okay, it goes actually in a linear fashion, not nonlinear fashion. So that is the constraint added to the natural spline. Okay, so outside the range of the boundary, it should go linear ways. So it goes with the tangent. So in that way, still it might have some boundary effect, but that boundary effect is much smaller compared to like using the cubic spline, the B splines. Okay, so that's the purpose for the natural spline. By doing that, actually the natural spline saved some degrees of freedom. How many degrees of freedom do we save? If we use a cubic spline, okay, a natural cubic spline saved 4 degrees of freedom. And you may ask, why we need to save the 4 degrees of freedom? Because we have 2 constraints. One is the cubic order. One is the quadratic order. The cubic and the quadratic order, they are all have the coefficient equals to what? Equals to 0 outside the range, outside the boundary. So we saved 2 degrees of freedom. One from the cubic, the coefficient for the cubic order, one from the coefficient from the quadratic order. But that's just from the upper side, upper limit. Also, we saved the 2 from the lower limit. Is that right? So we have 2 and 2. So we saved actually 4 degrees of freedom. Okay, so natural spline can spend more profitably by sprinkling more knots in the interior regions if we use the same degrees of freedom as B splines. Okay, so now let's see. So this one shows the pointwise variance. That shows the boundary effect. Okay, so you can see if we use the global linear, that's very safe because linear function doesn't hurt too much outside the boundary. Okay, because it goes linear fashion. It cannot go very quickly up or down, right? It's a linear. But if we do the global cubic order and the natural spline with 2 knots, you can see it can go very high for natural spline cubic knots, the green one. You can see when we reach the boundaries, the variance goes super high at the boundaries. You see that? So that's the boundary effect from the cubic splines. But when we use the natural splines, that is much better than the cubic spline with 2 knots like the B spline. But it's, of course, it's worse than the global linear model but it's more flexible than the global linear model. So the natural spline is somewhere between. It's not too bad. It's much better than the cubic spline, piecewise cubic spline, and it's more flexible than the global linear model. So this just shows you the boundary effect. And this shows you the basis for the natural spline, which very similar to the B-spline. Okay, and you can get these B-spline bases and natural spline bases. You don't need to worry about how to get these bases. There are math behind that. I'm not going to talk about that, and you don't need to know that. And but you can do these plots very easily because in the R, there is a function called BS to do the B-spline, and the NS to do the natural spline. So the computer will calculate these for you. And also both of them are computationally very efficient. And this just shows you an application of using the B-spline and natural spline, and also show you the benefit of using the natural spline comparing to the B-splines. Okay, so this data set is called old faithful geyser example. So we have the duration as the horizontal axis, X, and the response is the waiting time. Okay, so these blue circles are the observed data points. So here, this is the code that I used to generate these two plots and to create the two models. Okay, so here for both model, I'm modeling using the B-spline with degree of freedom is 10, and natural spline with a degree of freedom is 10. So both are 10. Okay, so you can see here, we have a B-spline, degree of freedom 10. So natural spline has degree of freedom 10. So they have the same degree of freedom. So how many extra knots we can have for using the natural spline? How many? We can have 4 more natural spline interior knots. Why? Because the natural spline relieve the cubic term and the quadratic term outside the boundaries in the upper limit and below the lower limit. So it saves 4 degrees of freedom. And these 4 saved degrees of freedom can be used to put 4 more interior knots. Does that make sense? But for the B-splines, it does not have that constraint that it goes beyond the boundary, it goes linear. It does not have that constraint. It still goes in a cubic splines outside the boundary. So that's why it has 4 less interior knots. Okay, so now let's compare the two fitted plots using the same degree of freedom. So if you look at closely, you can see here, outside the range, the natural spline goes in a linear fashion. You see that? But outside the range for the B splines goes to a nonlinear fashion. You see that? This one seems to be linear, but this one definitely you can see the nonlinear trend, right? So, but when we look at the interior part, let's say when we look at here, right? You can, if you look at closely, you can see the natural spline fitted curve is more what? Has more curvatures in it, is more flexible compared to the B splines. So the B splines are more like a linear fitting within the range. But for the natural splines, it shows more curvatures because what? Because it has more interior knots. If we have more interior knots, of course, the fitted curve will be more smooth and more flexible, can include more curvatures. Does that make sense? So that is the benefit of using the natural spline. And both models have the same degrees of freedom. In other words, both models have the same model complexity. They have the same model complexity, but this one is more flexible. And within the range and also more stable outside the range. So that's why in practice, people use natural splines more than the B-splines. Okay, so that's the natural spline. Okay, now here, but still natural spline, B-spline still has some problems. Why? Because you can specify the degrees of freedom. And after you specify the degrees of freedom, we place knots based on the percentiles, or user can define the knots. But still, that's subjective. Why? Because how many knots we should have? Or what is the degree of freedom we should have? Why we need to just put on these 7 interior knots or maybe 5 interior knots? Why not more than that? Why not less than that? Right? Still, people can find the subjectiveness. Okay, so now let's say we have a very, very objective approach. And that's called the smoothing splines. So smoothing splines is to avoid the knot selection problem in the regression spline that we talked about before. Because the smoothing spline use a maximum set of knots. Okay, so what is smoothing spline? Smoothing spline considers this question. Okay, so what is we want to find a function f. Okay, so what is the requirement for the function? We need that function to be smoothed and up to the second order derivative. So it has to be continuous up to the second order derivative. Okay, so that's the class of function we are looking for. Okay, and for this class of function, we want to find the one that minimizes this. Okay, so what is that? Let's say we have 2 parts, right? What is the first part? The first part is just the sum of squares error. Is that right? It's just the observed y minus the fitted value and take the square, take the summation. That's the sum of squares error, right? And what is the second part? The second part is the integral for the second square of the second order derivative of the f from a to b. So what is a and b? A and b are the lower bound and upper bound for the x. Okay? And then we multiplied by a tuning parameter. So tell me if f is a linear function. If it is a linear function, then what is the second order derivative for a linear function? I think that's an easy question, right? A linear function, if you take the second order derivative, it will be 0, exactly 0, right? And then we take the square, still 0. And then we take the integration, still 0. And then we multiplied by the constant lambda, it's still 0. In other words, this term is gone, is 0, when the function is a linear function. And what about constant? Of course, it's 0 again, right? So now you may understand what is that term about. This is catching what? Catching the curvature of a function. So what type of function f will give us the large value for the second term? Can you write out some function which will give us large numbers, large value for the second term? I can show you some. If the function looks like this zigzag, very complicated, this will have a large value on this. Why? Because first of all, it's nonlinear. Second is you can see the change on the first order derivative and second order derivative a lot. It has a very complicated curvature. So the f So the second order derivative changes from positive to negative, negative, positive, negative, positive to negative a lot. So when we take the square and take the integrations, that term will be huge. Okay, just in simple term, the second term is a penalty. Penalize those model with very complex curvatures. Up to what? Up to the linear function. If it's a linear function, no penalty at all, totally fine, zero penalty. If it's nonlinear, it starts the penalty. More flexible, more curvature, more penalty. Okay, so what about the first term? The first term is measuring the goodness of fit, how good the model fits the data. So you can now recognize that, oh, we see something very similar before, right? Do you remember? We see something. First, let me remind you, we have talked about those information criteria. Remember, we have the AIC, BIC. What are these AIC, BICs? The first term is about -2 log likelihood. And these are just like this term, how good the model fits the data is. If the model fits data very well, the first term will be small. If the model fits the data very poorly, the first term will be large. Is that right? Plus, what are this second term in the AIC, BIC? We have a penalty term, right? For the AIC, we have the 2 times the number of parameters, right? If we have more parameter in the model, of course, we have more penalty. So you can see this idea is similar to the AIC, BIC. And plus, it is very similar to what? Lasso, ridge, elastic net, we also talked. Remember, what is the lasso, ridge, elastic net? So what's the first term? The first term is just like that, exactly the same. That's the SSE. The first term is SSE for the lasso penalty. Remember? Plus, what is the penalty term? The penalty term is for the ridge. It is the summation for the beta j square. So that's also called the shrinkage method. And we have a multiplied by a lambda. So this is a penalty on the model complexity. If the beta are close to 0, the model is simpler, the penalty is smaller, right? So you can see all these concepts, and I can show you later in the artificial neural network, in the deep learning, okay, in the ChatGPT models, in large language models that you heard from the ChatGPT, Google, Gemini, they use this idea. Okay, so no matter how fancy the model name is, this idea is very, very useful, popular. It's using everywhere. Okay, so that's the point of why I remind you this. Okay, and this idea has a name called the regularization. So the idea is very simple. First, we want the model to fit the data well. But just having this first term is no good. Why? Because that can lead to overfitting. The model can fit the data very well, but the generalization is no good. So we need to have a balance. It's like a check and balance. So the balance term, that's the second term, is we also need to penalty. We also need to penalize on those models that are too complicated. So you can see what is the best strategy. The best strategy is just like the bias variance trade-off. We want the model to be very complicated so that it can fit the data well, but not too well, because we also have a second term, penalty. If it's too well, if it's too complicated, that may be overfitting. So we have a penalty on the model complexities. Okay, by combining these two, that idea can be applied in everywhere. in the machine learning statistical modeling. The form may be different, like here the smoothing splines using the integrals, and the lassos use the summations and so on. Information criteria use different, but the idea are all the same. So that's why getting the idea is much more important, much more critical to learn those details, because you know the idea, you know what's going on. Okay, so then if the lambda is 0, so lambda is what? Lambda is the balancing point. Okay, lambda is called a tuning parameter. It tunes the model, the optimal model that you want is close to the prefers to have the complicated models or prefer to the simple models. And that can be tuned through the size of lambda. Okay, so if lambda is 0, what does that mean? If lambda is 0, that means there is no effect or there's no penalty on the model complexity. So that leads to what? F can be any function that interpolates the data point, can pass through all the data. So that's the lambda is 0. When the lambda is infinite, that means it has to be 0 for this integration. That means F, the second order derivative, has to be constant 0. So that means it's a linear regression model. So now you can get the idea is, if we want to have a model which is complicated, we should choose a large lambda or small lambda. If we want the model to be complicated, the lambda should be what? Smaller. Because small lambda means we have less penalty on the model complexity. So the final model, the optimal model, will be more complicated. Is that right? So when we prefer the simple model, so the lambda should be chosen as what? As a large value, because that means we have a severe penalty on the model complexity. We strictly enforce the model should be simple. Is that right? So then the next question is, how do we choose the lambda? How do I know we should have a complicated model or simple model? Is that right? To answer that question is also very simple, because we learned what? Last week, we learned the model assessment. Remember? How to evaluate the model, how to assess the model. One of the techniques that I mentioned a lot is what? Cross-validation. You remember that? Cross-validation. So it's easy. We just use cross-validation to help us to identify which value of lambda we should use through cross-validation to choose the optimal value of lambda that minimize the cross-validation error. So the problem solved. So now you can see there is an automated algorithm there to help us to find a nonlinear smoother. Okay, but here it's not end here. We don't know the solution for this. This looks like fine, good objective function, but what is the solution? Can we solve that easily? The answer is yes. Okay, first I want to warn you that this solution at first sight is very complicated, because I know some of you are from the math department. If you take any functional analysis in the math department, you know that most of the function space are infinite dimension. Like there's a name called a Hilbert space. Okay, so if we look at the functional space, infinite dimension. Okay, very hard to find the solution because it's infinite dimension, not even finite. Okay, so however, it turns out that the solution for this optimization is extremely simple. We have proof for that, okay, rigorous proof, and that proof actually has based on a very famous theorem called the representer theorem. Okay, so the representer theorem shows that even though the criterion that we showed here is defined on an infinite dimension functional space, it ends up with an explicit finite dimensional unique minimizer. And what is that unique minimizer? The unique minimizer is a natural cubic spline with knots at every unique value of x. You see that? The solution is simple and also objective. Excellent. First, it's very simple to model. It's just a natural cubic spline with knots at the unique value of xi. And the second is it removes the knot selection bias. There is no subjectiveness anymore because we select every unique value of x appeared in the data set as the knots. Okay, so then you may ask, wait a minute, that may cause overfitting. Is that right? Possibly. But don't forget that we have a lambda here. So we can choose the lambda wisely through the cross-validation so that we can avoid overfitting. Okay, so that's the simple solution. Okay, so and I will just skip that. So this math just show you how to calculate the solution. The solution actually has an explicit form. So you can see we can write out the solution in the matrix form. So we have a closed form simple solution for this optimization problem on an infinite dimension functional space. And that result is based on a famous theorem called representer theorem. Okay? Okay, now let's see how do we choose the lambda. Okay, so the solution f hat can be written as an s lambda y. Okay, if we have s lambda y, so we have a subscript lambda. What does that mean? That means S is a projection matrix, which is a function of lambda. So S is a function of lambda, but a projection matrix. So remember, I showed you these forms before. So if we have a model, we can represent the y hat through a projection matrix times a y. And this model is called what? Remember that? We talk about that in the leave one out cross-validation. Remember, when we talk about leave one out cross-validation, I said when we have a certain model which can be represented by S times Y. S is a projection matrix. This is called a linear fitting model. So linear fitting model, this is exactly the linear fitting model. So linear fitting model doesn't mean it's a linear model. It's a nonlinear model. This is nonlinear, but it's still called a linear fitting. Okay, so then for this one, we can have an effective degree of freedom, which is the trace for the S lambda. So what is a trace? Okay, that is a very simple concept in the matrix algebra. If we have a squared matrix, let's say m by n. Okay, since it's squared, we have a diagonal term, right? So the summation of the diagonal term, the sum of the diagonal term is called the trace of that matrix. Okay, so this is called effective degree of freedom. And we can choose the lambda through the cross-validation or generalized cross-validation. Okay, so now let's see. For the cross-validation, we use leave one out cross-validation. Why? Remember, if the model is linear fitting model, then the leave one out cross-validation, we have a shortcut to get its solution. So the leave one out cross-validation for the linear fitting model can be simplified by just fitting the model once using all the data points. And that's how we get the leave one out cross-validation. So this is a shortcut. We don't fit the model multiple times, just one time with all the data points. And using this formula, we can get the leave one out cross-validation error. Okay, and this is the ith element in the diagonal term. But still, this is not the most efficient algorithm. Okay, this is not the most computationally efficient. We have an even simplified version that's called the generalized cross-validation approximation. So this is to approximate this value through by replacing the SII, the ith element, by the average of the ith element, by using the trace divided by the n. So just replacing the SII by this term. Why? Because this can be even faster in the computations for the GCVs. Okay, so that is the most computationally efficient way to find out the cross-validation results. Then we just choose the lambda that can minimize the GCV or minimize the leave one out cross-validation. Is that clear? We choose the lambda to minimize that. That's how we choose the optimal lambda. Okay, so that's the cross-validation. So let's stop here. Next part is I will show you some example. We are running close to the 250. So why not we stop here and I can start next time and we can go over quickly. And before next class, just read the notes so that we can move on quickly. Okay, any questions before we stop? Okay, so let's stop here.